Okay. One, two, three. Test, test. Test. Test, test.
Give it one because it's lagging.
Test, test. Okay.
I'll just make sure because it's now streaming this screen on this one. I'll check with them and come back in 1 minute.
Okay. Hello? Hello? 行 OK。
Make sure.
Testing, testing, testing.
Is it okay? Okay. So I classify existing techniques into two categories. One is how we can reduce n, which is the number of tasks. The other is how we can reduce the cost for each task. And the database community is mainly focused on the first part. And the second part is the main focus of the HCI community. But I will talk both of them. Let's first talk about how we can reduce the number of tasks. The first technique, we call it task pruning. The basic idea is quite simple. Think about that you have 1,000 tasks, and you cannot afford asking crowd to do all of them. You want to reduce the number. And the key idea is maybe some tasks that machines can do very well. You really don't need a crowd to do that. So the question is how we can quantify which task is very difficult, we need to ask the crowd to do, and which task is very easy, and we can ask machine to do that. So here I give you two examples about easy task and hard task. Suppose your goal is to decide whether the two strings are the same or different. Look at the first one. It doesn't make any sense to ask crowd to do it. It's a waste of money, right? So machines can do it very well. But for the second one, it's more difficult. Maybe it's worth asking the crowd to do that. Okay. So now the challenge is how we can quantify the difficulty. And fortunately, for many machine-based techniques, they can usually give us the uncertainty about the answers. For example, here, we can use the similarity value to see which task is the easy task and the hard task. For example, the similarity between the two strings are almost equal to 1. And the machine is very confident about this result. We don't really need the crowd to check it. Okay? So that's one idea. The other idea is to use machine learning. Because a lot of machine learning model, instead of just do the classification, they can also tell us the uncertainty about their result. For this particular task, we can model it as a classification problem and train a classifier, and then to use the distance between your data point to the classification to decide whether it's a difficult task or easy task. Okay? So here's the workflow about task pruning. So suppose you have 1,000 tasks. The first thing you need to do is to quantify the difficulty of each task. Once you get the difficulty of each task, you set the threshold. And then you remove the tasks which is below the threshold, which are the easy tasks. And for the remaining one, you ask the crowd to do that. Okay, very, very simple. Let's see what's the advantage of that. The advantage is it works for a wide range of applications. Because think about that, for any hard problems that you can think of, there must be already a lot of existing machine-based techniques to solve it, like entity resolution, sentiment analysis, image labeling, right? So many, many machine-based techniques. You can use those techniques to do the first pass over all the tasks you have. And then for the tasks that those machine-based techniques that are not very certain, you can ask the crowd to verify that. But the disadvantage is it only works for easy tasks. For the tasks that machines cannot do well, it will not help. Okay. So later I'm going to present 3 techniques that will work for difficult tasks. So imagine you have 1,000 tasks. You use a task pruning to prune 900 tasks. There's still 100 difficult tasks. How can we further reduce the cost? This sounds like a magic, right? So you have 100 difficult tasks. You can still improve the cost in this situation. So the first idea is called answer deduction. So the key idea is that there might be some relationship among the answers of these tasks. And once you get the answers of some difficult tasks, you can use the answers to deduce the answers of remaining tasks. Here's a concrete example. Suppose you have these 3 tasks, and look at them. So you're going to decide whether they are the same person or not. they are not very easy tasks, right? For the first one, this is Tracy McGrady, this is Will Smith. They look similar, but they are actually different person. So these two pictures look quite dissimilar, but they are actually the same person. So all of them are very, very challenging tasks. And we can use this idea of transitivity to reduce the tasks. Say the crowd tells you these are two different persons, and the crowd tells you they are the same persons. You don't need ask the crowd to check to do the task anymore, right? Based on the transitivity, you can deduce that they are the different persons. So using this idea of answer detection, you can reduce the cost. And the workflow of this technique is to use an iterative workflow. It will first pick up some tasks, and then use the crowd to get the answers to these tasks, and then use the answers of these tasks to derive the answers of remaining tasks. So say you have a task pool that has 10 tasks, and you first pick up 3 tasks, and you ask the crowd to tell you the answer to these 3 tasks, and you get the answers, and you use the answer of these 3 tasks to deduce the answers of some of the remaining tasks, and you know the answers of the 2 tasks. Then there are 5 tasks left, and then you go to the next iterations. Okay. And the advantage of the technique is it works for both easy and difficult tasks. But the disadvantage is it can make your human error be amplified. So imagine that human make a mistake about the task. And this error will be amplified because you are going to use transitivity to deduce the answer of this task. Because they tell you they are equal, this is equal, and the transitivity will tell you this is equal, but this is actually wrong. Okay, so that's the disadvantage of the technique. All right. So, another technique that can work for difficult tasks that we call it task selection. So the idea about task selection is you have a budget. Say you have 100 difficult tasks, but you can only afford asking crowd to do 10 tasks. The question is how you can make the best use of this budget to decide which task should you ask the crowd to do that. So that's the key idea of task selection. So what you need to do is to decide among these 100 tasks, which are the most beneficial tasks to crowdsource. And in order to define the benefit of each task, and it really depends on the goal of crowdsourcing. If your goal is to train a machine learning model, and you probably can use the active learning to determine the benefit of each task. Okay, so are you all familiar with active learning? Is there anyone how many of you have heard of active learning? Okay, I can explain to you. So this is a supervised learning, so which means you have a lot of data points on this plot, and you want to build a classifier to classify the blue points and the red points. But supervised learning requires you to label all of the data, then you can train the classifier. And active learning means you have a lot of unlabeled data, and it has a budget. Say I can only afford labeling 10 data points. And active learning can intelligently decide which points should you ask the crowd to label such that you can train the best model within the budget. So the key idea is here is that suppose you have already built a classifier in order to decide which data point you should pick next. So there's a technique called uncertain sampling. We'll pick out the data point that is close to this classification hyperplane. And if it's close, it means it's very uncertain. And then you will pick up those data points to label. Okay. So as I mentioned, it depends on the goal. If your goal is not to train a machine learning model, if your goal is to get the top K results, say you have 5 images, and you want to know which image looks most beautiful. So that's a different goal from training a machine learning model. Then you have to have a different way to define the benefit of each task. For example, if you have 5 images and you use computers to get an OK ranking of these 5 images, and this is the most beautiful one, this is the second most beautiful one, and you want to know that if you only have a budget to do one task, which task should you ask the crowd to do? Maybe you will ask the crowd to compare the two images, because that will give you the most information. Okay. And task selection, the workflow of task selection is also intuitive. So the reason for that is quite intuitive. Imagine you have a budget. It's like you are doing investment, right? So you have a budget of $10, and instead of spending all of $10 at once, you want to progressively investing the money. That can give you the most benefit. So the intuition here is that you want to crowdsource a small number of tasks and get the answers of those tasks, and then figure out that which task should be crowdsourced next. Okay. And the advantage of this is it gives you a very flexible trade-off between cost and quality. Because you can define a budget, then you can only spend this amount of budget to get the best quality. But the disadvantage, it will hurt the latency. Because at any iteration, only a small number of tasks available in the crowdsourcing platform. Although there may be thousands of workers, but only say 10 tasks available in the crowdsourcing platform, they can do that. So you didn't make full use of the crowd to do your task. So it will hurt the latency. Okay. So the last technique about how to dealing with a difficult task is called sampling. So in fact, this idea hasn't attracted a lot of attention in the crowdsourcing research area, but I personally think this can be a more and increasingly important topic, because as you may know, that approximate query processing is considered as one of the key challenges about that one of the grand challenges in the SIGMOD of this year. So given that AQP is going to be become more and more popular, I personally think sampling can attract more attention in the crowdsourcing area. So the key idea about sampling is quite simple. Say you have a very large data set, and you cannot afford crowdsourcing to do all of the data. So you create a sample of the data, and only ask the crowd to work on a small sample of the data. So here is a very interesting example. So imagine that you are a data scientist, and you want to know that among these 3 authors, which one published the most number of publications. And then you get the data from Microsoft Academic Search, and you see that, okay, so Professor Michael Franklin published 561 papers, then I will see that he published the most number of papers, and that's my result. But it turned out that the data is very, very dirty. So after we clean the data, we find that, in fact, it's not Professor Michael Franklin, it's Professor Jeffrey Allman published the most number of papers. The reason for that is there's many papers that were not published by Professor Michael Franklin that were falsely included into his publication list. And also, there might be some duplicate publications. So if you don't use sampling, you have to clean all of the publication to check whether this paper was published by Michael Franklin, whether this two papers are duplicated or not. That's going to spend you a lot of time. And by using the idea of sampling, we found that by only clean a small sample data, so this is the total number of publications you need to clean. By only clean a small number of publications, we can get a very high quality. So we found that by only clean 1/3 of the publication, we can get almost 100% quality. So the reason that we can do that is, think about that. So there's 561 papers, and some papers are not published by Michael Franklin. And when you look at, say, 100 papers, and based on these 100 papers, you see, okay, maybe 30% of papers are not published by Michael Franklin. And then you can use this 30% and multiply by this number. Then you can get a good estimation of how many papers that Michael Franklin really published. So that's the key idea that why sampling works. And the workflow for sampling-based method is still iterative, because you don't know what should be the right sample size at the beginning. And so you first create a small sample of data, and you ask the crowd to work on this small sample of data. And then you see that, okay, I get a result and try to figure out whether this result can satisfy my quality constraint. If it doesn't satisfy, you can enlarge your sample size and ask the crowd to continue to work on a larger sample. So the advantage of these techniques is because sampling has been extensively studied in the statistic literature, and there's a lot of techniques that can give you provable bound for quality. For the previous example, let's say if you only clean 1% of data, it may give you an answer like this. This is an approximate answer. So this is a confidence interval. It tells you that the true answer is within this range with probability of 95%. So you can use this answer to decide whether should I continue to clean more data or I should stop. Because that's a very, very good result that the other techniques that cannot give to you. But the disadvantage of sampling is it will only work for a certain type of queries. For example, you can use sample to estimate average sum, but you cannot use sample to estimate max, because max is very sensitive to a single record. Okay. So that's the disadvantage of sampling. All right, so that's the 4 techniques about how we can reduce the number of tasks. And the second category about cost control is how we can reduce C, which is the price you paid for each task. Say right now you pay $1 for each task. And I want to say I want to only pay 5 cents for this task. You cannot just tell the crowd, say, hey, I do not have enough money, and right now I pay you $1, and now I can only pay you 5 cents. That will not work, because crowd will choose a task based on how much money they can earn based on by doing these tasks. If you pay only a little bit of money, they will not choosing your task to do. Okay. So the key idea of task design is how to optimize user interface. And there's 2 advantages of optimizing user interface. One advantage is it can reduce the work time. Suppose a crowd worker spent 1 minute on your task. If you optimize the user interface, it may only spend, like say, 10 seconds on your task. Then you can pay this crowd worker less money for this task. Okay. So here is the example. So imagine you have these 6 images, and you want to know how many images are female. Okay. So that's one way to design your task, which means for each task, you ask the crowd to tell you is it male or female. And the crowd will say, okay, this is a female, this is a male, and after label 6 images, they can submit their task. And it may spend them, say, 1 minute to do the task. But you can also design an interface like this, right? Because you only want to know how many images are female. You don't really need to know which image are female or which image is male, right? So you can design this task to say, okay, tell me among these 6 images, how many are female? And crowd can only tell you a number instead of labeling every image. So obviously, this task will spend less time on this compared to this task, right? So then you can pay less money for the crowd for doing this task. So another even more crazy idea is, can we ask the crowd to do some task for free? We don't need to pay them any money, so which means we can do all of the tasks for $0. So the key idea is, because money is only one of the incentives for crowd to do your task. There are many other incentives. Think about that. How much time we spend in playing games, right? So we play games for fun, not for making money. And so why can't we design a game for the crowd such that they can have fun by doing this task, and they don't just do this task for money? So basically, this on there, Louis and Laura designed very, very interesting a game called the Yes Game in early 2000s. And the idea about this game is it will show you an image and ask you, what can you see in these images? And you can say, okay, I can see a lot of trees, I can see grass. And at the same time, there's another player who is also playing this game. And if you guys say the same word about this image, you win the game. So the less time you spend in figuring out what's a common word to describe this image, the more score you can get from this game. Okay? So, and this game was required by Google, and Google uses it for labeling millions of images. So very, very interesting idea. All right. So in summary, what I talk about the causal control. So I basically talk about, there's two directions about causal control. And one is how we can reduce the number of tasks. The second one is how we can reduce the task price. Okay? And in the database community, most of the research papers are focused on how we can reduce the number of tasks by assuming each task costs the same amount of money. And in the HCI community, they try to optimize the user interface to reduce task price. And we believe that the database community and the HCI community should work together. And that because in reality, your goal is just to reduce the cost. You don't care about how to, is it because you reduce the number of tasks or reduce the task price? If you combine the two ideas, usually it can give you a better result. And I also talk about different kinds of workflows for causal control techniques. And we found that both non-iterative and iterative workflows are widely used in reality. So that's all I want to talk about causal control. Before I move forward, is there any question? No? Okay, great. So latency control. So what's the goal? So the goal is we want to reduce the latency. So imagine you have a problem, you ask the crowd to solve this problem, and right now it spends you, say, 3 days to solve the problem. You want only spend, say, 1 hour to solve the problem. If you have this requirement, and what the latency control techniques can help you. Okay. And let's see how we can calculate the latency. So latency is the number of tasks multiplied by the latency of each task. Did you find any issue about this equation? Do you think it is correct? No. So why do you think it's not correct?
Each pass has different latency. Okay, not just multiply them.
Mm-hmm.
Some done in parallel.
Yeah. So in fact, they are done in parallel, right? Because there are maybe hundreds of crowd workers. So this is not the right equation. Okay. So it's different from causal control. That makes this part very, very exciting. So what should be the right equation for latency is that it should be the completion time of the last task. Say you have 100 tasks, and you publish them to the crowdsourcing platform, and the workers will do it in parallel. And the last task, the time you receive the answer of the last task is the latency of your entire job. Okay. That requires you have a different mindset to solve this problem. So I classify existing latency techniques into 3 categories. The first one is assuming that we only have a single task. Our goal is to reduce the latency for this single task. Okay. The second scenario is assuming we have a batch of tasks, say 1,000 tasks, and we want to reduce the latency of the slowest task in this batch. And the third scenario is assuming that we have multiple batches, and the goal is to reduce the latency of the slowest task in the last batch. So that's the 3 scenarios. But one thing I want to say is the techniques that work for a single task can also be applied to single batch, multiple batch scenarios to improve their latency. And the techniques designed for single batch can also be applied to improve the latency for multiple batches. So let's start from the most simple one, which is assuming that you only have a single task, say label an image, how we can reduce the latency for labeling a single image. Okay, so once you get the image, you are going to publish it to a crowdsourcing platform. But it's not often the case that the crowd worker will come to your task and do it right away. So usually there's some time called recruitment time, which is time that you spend in recruiting a worker come to your task and do it. And the second phase, I call it the qualification and the training task, because it's maybe the first time for the worker to do your task. And you need some time to train this worker to be able to make sure that this worker can give you the high quality answer. Okay. And the third one is the actual time that the worker spend in labeling this image. So in order to improve the latency for single task, what we really need to do is to reduce the time spent in recruiting, the time spent in qualification and training, the time spent in labeling this single image. Okay. So I'm going to talk about how we can reduce the recruitment time in the next slide. For improving the second phase, which is the qualification and the training time. So in order to figure out how to improve that, let's first think about why we need qualification and training time. The reason for that is we want to make sure that this worker can give us high quality answers. So that's actually one of the quality control techniques that Yudian presented just now. Okay. But Yudian also presents many other qualification techniques that we can use, right? So if you think this is a bottleneck, you can just let the worker to do your job, and then figure out that which worker is a bad worker later by applying some other quality control techniques. Okay. So how we can improve the third phase, which is the work time. So as I mentioned before, that we can design a better user interface that can reduce their work time. Okay. So now I'm going to talk about how we can reduce the recruitment time. So the idea is very, very simple. Because you know that you are going to spend a lot of time in recruiting, why can't you just pre-recruit those workers and maintain them? And once you have something to do, and just ask the pre-recruited worker to do that. It's similar that you are going to start a company, right? So you usually recruit a lot of people, and then you have a task want to do, you ask those people to do that, not the other way around. But the tricky part is how we can implement it in crowdsourcing platform. How we can implement this idea of pre-recruiting in crowdsourcing platform. And Michael Bernstein, who is now an assistant professor at Stanford, did a very cool project when he was a PhD student at MIT. And his idea is, okay, so, sorry, so there's some technical issue that do not allow me. Okay. So his idea is, okay, so let's first publish this pre-recruitment task. And we publish, say, 10 tasks. For each task, it's like this. Worker will see, okay, so I don't need to do anything. I just need to wait here. And I'm going to get paid half cent per minute. And I'm going to get a notification with 5 minutes. It turns out that a lot of workers like this kind of task because they just need to open up a web page and didn't need to do anything, and then they can make a lot of money for doing that. Okay. So once you have some task for worker to do, it will send a notification to those pre-recruited workers like this. Say, hey, there's a very exciting task. Would you like to work on that? And the worker will see, okay, so it seems the task is very interesting, and they will click, if they click this link, they will go to that task. Say that task is labeled an image. And they can work on those tasks immediately. So this idea actually reduces the latency about recruitment. So very, very interesting idea. All right. So now I'm going to talk about how we can reduce the latency for single batch of tasks. Say you have these 7 tasks. You're going to reduce the latency for the slowest task. So one idea is, let's predict which task is the slowest. And we can increase the money for that task and attract more workers. So we call it a pricing model. But the challenge is how we can predict the task time. So you have to predict the recruitment time, and you also need to predict the work time. And these 2 papers talk about an idea that use a Poisson process to model workers, and then they can build a relationship between the task price and recruitment time and work time. And there's 2 papers so once you get the model, you know which task is the slowest. Then you can set the proper price for those tasks. And you can set a fixed price. Aditya and his student invented a very, very cool idea called dynamic pricing. That is, it dynamically set a suitable price for each task. They show that it can further reduce the total cost you need to spend. Okay. So the previous idea requires you to predict which task is the slowest, which tasks take you a lot of time to do. But sometimes you cannot make a very accurate prediction. Think about this scenario. So imagine a worker is doing your task, but suddenly this worker has a phone call. And this worker will answer the phone. You don't know that how long this worker will answer the phone, right? For example, if this worker's baby is crying while she is working on the task, and this worker will take care of the baby, you don't know how long this worker will spend on this task. So this is something that you cannot predict. But what can we do in this scenario? So there's a very cool idea called straggler mitigation from the distributed computing community. So the idea is as follows. So imagine that you have 2 tasks, right? So this task, you want to label them whether the cat or not. And it will replicate a task. So like the quality control idea that Yudian presented, you ask multiple workers to work on a single task. And you don't really have to predict that which task can spend more time. Whenever a task is finished, you will terminate the slowest task, right? So you don't have to say, okay, this might be the slowest task, I'm going to set a higher price for that. Or maybe this is the slowest task, I'm going to set a higher price. So this idea avoids making the prediction, but still can reduce your latency. So as I mentioned, this idea is being widely adopted in some distributed computing framework like MapReduce and Spark. Because the reason for that is, think about the difference between crowdsourcing and distributed computing. In the distributed computing, you have a job. And the way it works, it will split the job into multiple tasks and then ask, say, thousands of machines to do those tasks. Each machine you can think of like a crowd worker, right? So in the crowdsourcing world, it's similar, right? You have a very complex problem. You divide it into multiple small tasks, and you ask multiple crowd workers to work on that. So because they are very similar, so that's why we can apply some of the techniques that are being used in distributed computing world to the crowdsourcing world. Okay, so I talk about that, how we can reduce the latency for a single task, how we can reduce the latency for a single batch of tasks. Now I'm going to talk about how we can reduce the latency for multiple batches. So before we talk about, let's think about why do we need multiple batches? Why can't we just publish all the tasks at once? Why do we need multiple batches? Say you want to label 100 images. why can't you just publish this 100 image to the crowdsourcing platform? What's the disadvantage of doing that? Any thoughts? So it's to save cost. So as I mentioned in the cost control technique, we have some iterative workflow, right? So we first publish a small batch of tasks. We get the answers for those tasks. Then we figure out that which task should be published next. For example, this is one technique from the cost control category. So suppose you want to use the answer deduction to reduce the cost. If you publish, so there's 3 tasks, right? Decide whether they are the same person, decide whether they are the same person, decide whether they are the same person. If you ask the crowd if you publish 3 tasks to the crowdsourcing platform at once, then you will not be able to use transitivity to reduce the cost. So the ideal way is you publish this task, the crowd tells you they are not the same. You publish this task, the crowd tells you, okay, they are the same. Then you don't have to publish this task because you can deduce the answer of this task based on transitivity. Similar for active learning, it's also an iterative workflow. Okay. So we know that the reason that we need to publish multiple batches is we want to save cost. So then there's 2 extreme cases. One is that every time we only publish a single task, we are not going to publish more tasks until we get the answer of this task, which I call it single task per batch. So the other idea is we publish all the tasks in one batch. And the disadvantage of this technique is it will involve high latency because you only publish 1 task per batch, and there's only 1 task available in the crowdsourcing platform. And the disadvantage of this extreme case is it will suffer from high cost. It cannot fully utilize of the, for example, the answer reduction technique to reduce the cost. So the question is how we can better balance between the 2 extreme cases. So the first idea is that based on interesting observation, is it possible that we can increase the number of the tasks we publish per batch in the first situation without hurting the cost? For some problem, it works. For example, for the answer reduction, the transitivity problem, and it works. But for some problem, it will not work. And you may have to adopt the second idea, which is, can we model it as a latency budget allocation problem? Say you only have 1 hour that you want to get all the tasks done. And you model it as the optimization problem to decide what the number of tasks should be published at each iteration that can minimize the cost you spent in total. So that's the 2 ideas that you can reduce the latency. Okay, so in summary, a very important point I want to talk about latency is the way you compute latency is different from the way you compute the cost. The latency is calculated as the completion time of the last task. Okay, so I talk about 3 scenarios, and for each scenario, I talk about the different techniques you can reduce the latency. And one thing I want to say is that, for example, for the latency control techniques that work for single task, you can also apply it to single batch scenarios and multiple batch scenarios. And for the latency techniques that work for the single batch, you can also apply it to multiple batch scenario. Okay. So that's a summary of latency control. So the last thing I want to talk about is the 2 takeaway message about my presentation on cost control and latency control. The first one is there's no free lunch. I told you about a technique that can reduce the cost, but sometimes that you may need to, this technique may increase the latency or lower the quality for your problem. So you have to know that the trade-off that this technique can give to you when you decide whether you should use this technique or not. Okay. And the second key takeaway message is that crowdsourcing is a multidisciplinary research area. And in the database community, we are working on how to use the crowd to manage data more efficiently, more effectively. And in the HCI community, they are focused on how we can design tasks to make crowd to work, how to design a better user interface for the crowd to do our task. And there's many other community outside the CS field, like the economics and the psychology. They are also working on some interesting problem about crowdsourcing. So in this presentation, I talk about 2 ideas that from other communities that can be applied to reducing the cost or improving the latency. I believe that by collaborating with the researchers in other fields, we can have more interesting ideas to do cost control, quality control, or even latency control. Okay, so that's all I want to talk about cost control and latency control. Before I pass control to Ju, is there any question? No? Okay.
Okay. So testing. Okay. So it is my part to introduce the crowdsourced database management. My talk have 2 goals. The first one is I will let you know what do these crowdsourcing database systems look like. Okay. And the second goal is how the quality control, cost control, and latency control techniques are applied in the existing crowdsourcing database systems. Okay, my name is Ju Fan, and I come from Renmin University of China. First, I will mention a little bit about the motivation of crowdsourcing databases. Although existing traditional database systems have been successful for many years, there still exist limitations for them. Here is some example. The first limitation is about data missing, which is very common in the modern applications. Suppose we have a car table and we have a SQL query that wants to get Toyota cars. And unsurprisingly, this query will get nothing, right? Because the make information of the first record is missing. More technically, we can say that existing DB systems has a closed word assumption. As such, it cannot retrieve the record, which is currently not exist in the current database store, but actually in the existing world. The second limitation is about performing the machine hard tasks mentioned by Guoliang and other colleagues. Suppose we have 2 tables. The first one is a set of images, and the second one is a car configuration information. And we would like to, identify the images containing red cars and link these images to the car specifications. And the traditional systems are also not good at these tasks because the image detection and the data integration jobs between the images and the relational data are still very hard for the machines. Okay. So this motivates us to integrate the crowd functionalities into the DB community. And the basic idea is trying to extend traditional relational databases by asking questions to the crowd, so as to extend from closed world to open world and processing DB hard queries. Okay? So that is some quite high-level ideas of that. Along with these ideas, recent years has witnessed a couple of existing crowd DB systems, such as CrowdDB, Kirk, DECO, CDUS, and CDB. In the remaining part of my talk, I will introduce these systems individually, and due to the time limit, I will focus on the key features or the key difference of these systems. If you have any more questions, we can talk offline, okay? Oh, sorry. Before getting into more details, I will give you a high-level overview. The existing systems extend from traditional systems by applying a relational data model and SQL-like query languages. One benefit of this design is trying to enable existing SQL programmers easily use the cross-sourcing database systems. However, the key part of each system is trying to address the challenge of how to interacting with the crowd in a more effective and efficient way. So here is some more details. This is an overview of the query processing part. At the first glance, we can see that it's quite similar to the conventional way, like a SQL parser that parse from a query to an initial plan, and then a SQL optimizer can translate this initial plan to an optimized plan, but quite similar to the conventional way. But the difference are twofold. First of all, the operators in the query plan are cross-sourcing operators, which will be introduced later. The second one is the optimization goals are more complicated than existing DB systems because cross-sourcing have three optimization goals, the cost, the latency, and the qualities. So the first part of my talk will include the cross-sourcing query optimization techniques. And the second part of my talk is about how to design for each individual operators. In the cross-sourcing part, eventually, you have to translate an operator or anything you want to design into human intelligence tasks, or the HITs for short. That is just a user interface and a question interface for the cross-sourcing workers to answer, right? So the second part will be introducing how existing techniques can be applied in this operator-to-task translation process, okay? In the remainder of my talk, I will use this global running example consisting of 3 tables. The first one is a car review, which is just unstructured text. Although I highlight some attributes here, we should note that these attribute values could be extracted from this unstructured text. The second table is just a traditional relational data that's about car information. And the third table is consisting of a set of images. Example query could include find the black cars with high-quality images and positive reviews. For this query, it wants to integrate all the information from these 3 sources and make some filtering criterions. Okay. Okay, that is the outline. I will first introduce the system one by one, and then I will give you some high-level ideas of design principles of the operator design. CrossDB is one of the first cross-sourcing database systems. And the main focus of this system is trying to provide a systematic formulation of cross-sourcing process and its integration with the existing DB systems. To this end, CrossDB introduced CrossSQL, which is an extension of traditional SQL query languages. I will only focus on the difference of CrossSQL from the existing SQL languages, right? Okay. The main idea is they want the end users to use CrossSQL to define what things can be cross-sourced and what the missing data and which part of the missing data could be cross-sourced. Typically, there are two types of missing data. The first one is the missing columns, and the second one is about the entire table are missing. CrossDB or CrossSQL just use a keyword crowd in this create table statement to specify, okay, for this 3 columns could be cross-sourced, and for this case, the entire table could be cross-sourced. If you have insufficient number of tuples inside this table. The second usage of CrossSQL is trying to identify which part could be involved by the cross-sourcing workers to perform DB hard tasks. Actually, it defines 2 types of DB hard tasks. The first one is a crowd-powered filtering. For example, you want to identify the positive reviews, which means you need to involve a sentimental analysis component here, which could be easy for the machine, could be easy for the crowd, but may not be very easy for the machines. For this part, CrowdDB has introduced a new operator equal-to, which means this equal-to could be cross-sourced for the filtering purpose. The second one is a crowd-powered ordering. That is one example which is also mentioned by Jianan before. Suppose we have a collection of images. We want to sort these images according to the visualization qualities. Okay? And in the CrowdDB systems, it introduces a keyword crowd order to ask the system something like that, like I have a set of images. I want ask crowd to help me to order these images. Okay, to support this crowd-SQL semantics, CrowdDB focus on design some so-called crowd operators. For example, this is two types of crowd operators, crowd probe and crowd join, for this SQL query, which means the user wants to collect a set of Volvo cars. To answer this query, the system first uses crowd probe operators to fill more information of the Volvo cars. And this process will ask the crowdsourcing workers, give me some more Volvo cars and fill the detailed information of the cars. And then it will introduce a crowd join operator. That operator will, on demand, initialize some such kind of user interface to ask the crowdsourcing worker input some car reviews that could be joined with the existing car information data. And for the DB hard tasks, CrowdDB focuses on an operator called crowd compare. That operator asks crowdsourcing worker to compare two entities. And this operator can be fulfilled in two cases. The first one is to crowdsource equal to. For example, it gives you two entities, IBM and Big Blue. It will ask you whether these two entities are of the same entities. And this kind of entity resolution tasks can facilitate this equal to operator. And the second one is about order by, which is mentioned before. And that is it's a compare or pair with compare tasks, like to compare these two images and ask which one can visualize better the Golden Gate Bridge. This is crowd compare operators. Based on these query processing operators, CrowdDB also talk a little more about the optimization, but it just applies some rule-based optimizers, such as pushing down the selects or determining the join orders. Partly because there's quite a little about the query optimizations. The following crowdsourcing database systems focus more on the query optimizations, which will be talked individually in the remaining parts. The second system is Kirk, which is proposed by MIT. And we can see that the Kirk's query language are also an extension of traditional SQL query languages, but a slightly difference in terms of implementation is it's trying to use this UDF, user-defined functions, to incorporate the question, the question and the answer candidates, or the majority voting for this answer aggregation, as implementation details. And I would like to say that the most interesting part of Kirk could be is query optimization techniques by introduce better interfaces. Here is some examples for crowd join. There could be three types of interfaces for crowd join. The first one is just a simple compare. You give me a pair of entities. I just input yes or no. These two entities can be joined. Okay. The second one is it's called naive batch, and that means I can put a couple of compare-based questions into one HIT, and I can ask the crowdsourcing workers to answer them answers them all, and after that, I can pay the money, right? And the third interface is a little bit more about HCI. Like I can give you two columns of images, and you can link these two images just like a linking game. And when the linking is done, the images has disappeared, which means you have done this task. It's more attractive for the cross-sourcing workers. And according to Jiannan's suggestions, these types of interfaces could reduce the cost, while possibly may reduce the latency. And the second interface design for the cross-sourcing sort is more interesting. Like suppose I want you to give me a sort list or a top K images about which cars has a better visualization effect. There could be two possible interfaces. The first one is rating-based, and you can give me 6 degrees of the visualization effects and ask me to rate it, right? However, this rating-based interface may have a drawback that the ratings across different images may not be fully consistent with each other, right? For example, at the beginning, you could be very strict, but at last you are tired. You just, okay, so. Okay? So another better interface is about the compare-based one. And you just compare each individual images. And for this interface, the consistent issues may not be very significant, but it has to incur quadric number of tasks, which could incur less cost of the money. So Kirk has some very good ideas to how to balance between these two interfaces. And another very interesting part Kirk has introduced is about the feature filtering optimization, which is introduced by these keywords possibly. This idea is quite similar to some techniques in entity resolution. It means suppose I want to join this two images which may contain the same car from an image site, and I could get some possibility keywords and introduce some filtering features. And that means I want only filter the pairs with different makes and colors. And that means I only take the pairs with the same make and the same colors as the candidates of my joins. Okay? So, and Kirk also discussed whether a filtering feature is always helpful. The answer could be no, and I can give you some examples. The first case is about the balance between the filtering cost and the join cost. Different from traditional machine-based entity resolution, if you want to filter, if you want to use the filtering features to filter more candidates, you have to pay, right? You have to pay for the crowd. And that part will also incur cross-sourcing cost. So there's a balance based on the distributions of the underlying data. Suppose an extreme case, if all the cars have the same style, it could be a waste of money if we want to filter the style of each cars, right? Because they're all the same, and you may not be able to filter anything. The second example is about the feature itself. Some filters may cause false positives, which make this filtering attributes unsuitable for these join scenarios, because we want to find a set of correct answers, and we do not want to find the false negative parts. And the third part could be caused by the error-prone natures of cross-sourcing workers. If the workers have a disagreement about the filtering attributes, that filtering attributes could be of low quality to our join purpose. Okay. The third system is about DECO, which is proposed by Stanford University. And I think the key difference of DECO from the previously two systems is focused more on the data collection problems. Like I have some data missing problems. I want to collect more entities, or I want to fill more attributes, values of my data. To this end, it introduced a fetching process. And to make this fetching process better, DECO first separated a conceptual relation like car make model, door number, style, which is a user interval. user view, as a view to the end users. And it also introduced a raw schema, which is system view. And I will explain later that this view separation will facilitate the fetching process. And DECO also introduced some fetching rules to indicate how to collect the data. Okay? For example, the first one is I want to fetch a new car with the make and the model as its key, right? Okay. The second one is suppose I have a car, I have its make and model information, and I want to fill the missing door number information of that car. Similarly, this one could be the fill the style information of a given car. Besides the fetching rules, DECO also introduced some resolution rules. That is because the answer contributed by the crowd may be inconsistent with each other. So the resolution rules may include the majority voting and the deduplicate limitations. And that is one example of DECO SQL schema. We can see that it's quite similar to the SQLs, but there's new keywords min tuples that indicates how many tuples you want to fetch from the crowd. Okay, to support the fetching semantics, DECO has introduced the fetch operator, and that operator can be very naturally translated to this kind of interface. That is fetching a new car and fill the missing style information of the car and fill the missing door number information of a given car. And it also introduced some machine operators like scan, just like insert a new collected tuple into raw table and resolve majority voting or deduplicate eliminations. And the traditional join that could join the raw schemas together and to generate the concept relations. Here is one example. Suppose this is the current status of the existing databases. We have 4 cars, the make and the model information. And we only have 3 cars having the information of the styles. And the next, I will give you an introduction of how DECO can answer this query in a cross-sourcing schema. Okay, sorry. At the beginning, DECO will publish some fetching operators in the cross-sourcing platform. And from this part, you can see why DECO wants to separate the views, because it can fetch the entities and filling the attributes in parallel. And after that, it used some resolution rules for combining and aggregating the cross-sourcing answers. For this one, is just to fetch some new car information. So this resolution rules is deduplicate eliminations. That means we do not want to find deduplicate cars. For this latter 2 cases, the objective is to fill the style information or the door number information of the existing cars. So, it's just the rules is just for the majority voting. Okay, and for this join is quite machine-based join, and trying to integrate this 2 tables together, and and then further integrate this 3rd table, and at last get at least 8 tuples. And one key features in DECO query optimization is it introduced a cost-based estimation for this cost optimization. Due to the time limit, I would not go into details of this computation formulas, and we can talk it later. Okay, and DECO also discussed some better query plans, such as the reverse query plan. The idea is, can we use these attributes to reverse the entities instead of use the entities to fill these tuples? And the paper has shown that this review plan could incur less costs in the query. Okay, the first system is CDAS proposed by the NUS. And a key features of CDAS is it's trying to balance between the cost and the latency. And to this end, it has introduced 2 objectives. The first one is a cost minimization. Like, we do not care about the latency. We just want to minimize the cost, which is also studied in the previous DB systems, cross-sourcing DB systems. But the second optimization objectives are new. It wants to find a query plan with a bounded cost and a minimal latency. That means we want to save the money. At the meantime, we want to reduce the time of the latency. To this end, CDAS has some optimization techniques about the selection queries and a CFIL and CJoin framework for the join predicates and a latency-aware framework for determining the join orders. Here are some details. The idea of these selection queries is trying to balance between the cost and the latency. One extreme case of this selection is just a sequential plan, and we can ask these query conditions one by one. Each of are in individual runs. For this plan, we may save the cost, but the latencies could be quite high. That part is quite similar to what Jenna has said is about the iterative processes that could be incur multiple runs. And the second case could be the parallel case, and we can push all the conditions in one round, and we can get quite a low latency, but the money cost could be high. So CDAS has used some techniques to balance this cost and the latency trade-off. And for the join predicates, we can have two ways for the implementings. The first one is we can compare every pairs, and the second one is we can fill the missing join attributes, and then we use machine-based way to join them together, right? The innovation caused by CDAS is just like it has introduced a hybrid CFIL and CJoin way. The idea is it judicially selects some attributes for filling. For this intermediate nodes means fill the tuples with these specific attributes. And this lib nodes means then they use a compare-based CJoin way for compare each pairs of these tuples and get the final results. And CDAS has introduced some optimization techniques by I think it could be inspired by the traditional decision tree construction process. And at last, it has integrated all the tactics together for this very complex query optimization plans. Okay, CDB is a very recent work, and it's actually published in the SIGMOD in this year. And the basic idea of CDB is try our two parts, I think two innovations. The first one is a graph-based query model. The idea is, can we first build a graph on top of the data we want to join? Here is one example. Suppose I want to find all the images with the red cars, and we want to link the images with the car information and the car reviews. And we can first build such graphs of the existing data. Here, one edge means these two tuples could be possibly joined together. To building these edges, we can computing a matching probabilities for each cross-join, and then we can build a query graph that connect tuples if the matching probability is larger than the threshold. Then we can publish each edge to the crowdsourcing platform and collect the answers. We use this blue color to indicate that this the answer is yes, and we can join them together. This red color means the answer is no, we cannot join them together. And so the final result could be a path containing all the cross-joins. The second innovation introduced by CDB is all query optimization techniques. First, it focuses on the cost controlling part. The main idea is it's trying to selecting the minimum number of edges, which is quite different from the existing join ordering techniques. So here is one illustration of traditional way. In order to join them together, we first find the first join to be implemented, and that could be the second join. And we ask 5 tasks to crowdsourcing for the crowdsourcings, and then we prune other edges which could be useless for the following crowdsourcing tasks. Then the first join, and then the third join, and the total task could be 8. But for CDB, we can actually select these edges individually, and we do not care about what joint ordering is actually, these edges are actually in. And for example, we can first select the first edge and do this pruning, and this edge do this pruning, and then these three edges to connect them tuples. And we in total use 5 tasks. And this paper has proved this problem is NP-hard and introduced some heuristics to do that. And the paper also introduced the latency control. The main idea is to partition the graph into connected components and cross-source each components in parallel. And it also talk about the quality control. I think the main idea is quite similar to what Yudian has said. It's about the truth inference and entropy-based task assignment model, which is mentioned by my colleagues before. Okay, so this is takeaway for system design. Most of them use relational data models and extended SQL queries to support interactions with the crowd. And for the query processing, there are mainly 2 types. The first one is a tree-based model and graph-based model, together with the crop-powered operators. And the optimization could involve 3 goals, the quality, cost, and the latency. Okay, so next I will just briefly talk about the operator design. The difference between the first part and second part is the first part mainly focused on a global systems and well, take each operators as a building block. And the second part, we will get into more details of that building block and ask and talk about how this operators is implemented. We should know that the existing operator design has utilized the cross-sourcing techniques which are mentioned by my colleagues, like quality controlling, cost controlling, latency controlling, and task design techniques. Then I will just briefly talk each operators one by one. The first one is select. It's quite similar to the select operators in the traditional DB systems. But the difference is we need to use the cross-sourcing for the filtering criterions. The first work about the cross-sourced selection is trying to find all items satisfying some conditions. For example, find all images containing the SOV cars from image site. And the idea and the key idea of this work is similar to Yudian has said. What Yudian has said is truth inference, trying to say if I have collected 3 yes answers and 1 no answers, can we output pass or we output fail? And then is a task assignment. And if I have asked these 4 questions, do we need to ask more questions? That is a balance. That's a trade-off between cost and quality. The second word is how to balance about the cost and the latency. Okay, this operator only wants to find 2 images, the top 2 images, or any 2 images from 100 images site. Okay, actually we may have a couple of choices to implement these operators. The first one is a sequential task, like we ask each images one by one in different rounds. For example, yeah, and at least we find 2 images, 2 SUV containing SUV cars. In total, we have incur 4 questions and 4 rounds for latency. The second choice could be parallel, and we ask 100 images in parallel, and we got 100 questions and 1 round of latency. And absolutely, you may think there could be some hybrid way, like we first ask 2 images together in 1 round, and we identify successfully 1 SUV cars, okay? And now we only have 1 remaining cars to be found. Then we put 1 cars in the second round, fail. In the third round, okay, we found all the 2 SUV cars. The cost could be 4, and the latency could be, and the number of rounds is 3. And obviously, the third solution could be better. Okay, for join, for join operator design, they mostly use the techniques Jijian has said. It's about answer deduction. For example, use this transitivity rules and the task selection for selecting the most influential tasks as mentioned by Jianan. I will not get into more details about this part. For top K, it could be very interesting, because this choose inference are quite different from Yudian has said. Okay, the idea is trying to resolve the conflicts among the crowd. And suppose we have Jianan's example consisting of four photos, okay? And we can use the pairwise voting and ask the vote from the crowd. That means I ask 2 votes from the crowd. That indicates A is better than B, okay? Similarly, I can ask all the votes from each pairs in this data set. And we may observe 2 very interesting phenomena. The first one is there could exist so-called in conflict in this pairs. Two workers said B is better than C. Well, one worker said C is better than B, and one worker said B is better than C. You may think that we may just solve this problem in the traditional majority voting techniques, but you will soon observe that there could be global conflicts. For example, okay, there's 2 votes, so after using majority voting, B is better than C is better than B, sorry, and B is better than D, so we can infer that D is better than C. However, we also have another observation that there are 3 votes to support C is better than D, right? So there, in a word, there's both local and global inconsistency in this cross-sourcing votings. So we have to do the rank inference, which could be a very complex problem. Okay, the second work about top-K sort is about the task selection, which has been mentioned by Jianan. I just put it here for the completeness considerations. The third operator is about cross-source collection. And the key idea addressed by this operator is to infer when we get all of them. And that means we want to infer the item coverage. The idea is quite interesting. It has borrowed some ideas from the species estimation algorithms. The basic idea is if you have observed many new items in the beginning, that means we have far from the completeness. But if we have observed a very limited number of new items, okay, we could get them all, right? That could be some estimation algorithms from the statistic community. Okay, I know. This cross-source, in the cross-source collections, there are also task assignment techniques. The idea is we want to select some tasks satisfying some result distributions. This work is based on the observation that the workers may have diverse distributions about the entities they are contributing in. Some workers may give me some old-fashioned things, but while other workers may give me some new-fashioned things. So it's quite be beneficial if we can estimate the workers' underlying distribution and select the workers optimally to improve the performance. And that is operator for field. Okay, sorry, I just missed the citation here. It's a quad field in the SIGMOD conference. And the idea is just like very similar to Google Doc, and we can use a partially filled table with voting for filling this missing information in this table. And the last operator is crowd count. And Jianan has mentioned the key idea of this estimation techniques. So here the takeaway for the cross-sourcing operators. Each row means existing cross-sourcing techniques mentioned by my colleagues, and each columns means a cross-sourcing query operators. And you can, from this marks, how the existing operators utilize the existing cross-sourcing techniques. Okay. And finally, I will give you an summarization of the systems. This is the 5 cross-sourcing systems I have mentioned in my talk. And this mark has indicated how these cross-sourcing systems support the cross-source operators mentioned from my second part of my talk. And this is the optimization objectives supported in these systems. For example, we can see that CrowdDB focuses on cost and quality optimization, while it does not talk too much about the latency. Okay? And this is the design techniques and how the systems support the design techniques, which are mentioned by my colleagues. Okay, thank you very much for your listening. Okay.
Thank you.
sorry.
That's okay.
Okay.
I want to take it away. All right. I want to summarize our talk by giving some challenges, which I hope can give you some insights about the further development in this field. Now, during our research, we found that there are a number of problems that have not been really solved. So the first issue is a standard or systematic way of measuring the accuracy or the effectiveness of crowdsourcing. Now, you know, in traditional databases, there are already well-established benchmarks, okay, such as TPCC, TPCH, etc. However, in this crowdsourcing area, although the field has been becoming more important, however, the data sets are far from perfect. Okay? There are numerous reasons. Like, for example, the data sets that have been given have very few answers from the workers, and most of them are about single label tasks. And there are very few numeric tasks, and I'm not sure about other kind of tasks as well. So, and another problem is that whenever we do this kind of research, we very frequently will need to have some ground truth, right? Because at least in the controlled experiment setting, it would be desirable if someone tells us that, hey, your top K results will give you this kind of ground truth because some expert tell you that this is the case, all right? However, we don't really find such a data set, and one of the reasons is because probably in typical crowdsourcing tasks, there are a very large number of tasks, so it is very difficult and expensive to get ground truth from experts. And so this kind of like gives some obstacles to the very systematic and fair comparison of the algorithms. And the second issue is about scalability. All right? And in fact, although many of the efforts are trying to attack this problem, but if we are talking about there are thousands of tasks with many workers to work on, if we want to do a very good and fast optimization, this is still very difficult. Okay? And there are recently some work trying to attack this problem. However, the solutions are very problem specific. Like, for example, trying to attack active learning and entity matching problem. So can we have a more general framework that can have a scalable crowdsourcing framework is an open problem. And as Zhifan has also talked about some query optimizations that have been done in the crowdsourcing systems. However, compared with the very mature field in database systems, this problem study is far from complete. Okay? And especially as our previous previous speakers have talked about, in crowdsourcing, we generally face the problem of cost, latency, and quality optimization. And it's very difficult to balance all these three factors. And if you take these three factors into account of optimizations for crowdsourced queries, it is becoming very challenging. And another underlying problem is that humans are much more unpredictable than machines. So you can tell the machines that I want to optimize the performance of a query relatively easily, but if you want to optimize the crowdsourcing query based on the human input, which are far more unpredictable and error-prone, this becomes a very difficult problem. Okay? So, and the third problem is actually the truth inference problem, which we find that in our recent survey. Okay? There are no best methods, and sometimes we find that even the oldest method works best. Okay? So we still need to find better ways to try to see how we can do better truth inference. Okay? And then another emerging problem is about privacy. Now, because of the fact that the crowdsourcing systems are becoming more common now, okay? Now the privacy problems of requesters and the workers, okay, come into the picture. All right? So if you are a requester, how can you make sure that the questions that you design do not give too much sensitive information? So for example, if the questions are about patients, okay, you want to disclose some of the patient's information to the workers, but then how can you do it in such a way that you do not expose the patient's privacy? And at the same time, okay, workers have to give you some information about their interest or their expertise, and sometimes maybe the workers don't want to tell too much about themselves. Right? So how can you still attract workers to come to your systems? And how do you make sure that the worker's privacy is not interfered, right? And if some of the workers actively participate in the system, and in the end, okay, you can actually use their answers to try to find out who they are and try to find out what is sensitive to them, then that will also discourage the workers from using the system. Okay? And then the fifth point is that, okay, most of the work that we talked about so far in this tutorial about very simple tasks, like micro tasks, okay, yes or no questions, multiple choice questions, sentiment analysis. But there's not much done, okay, in terms of macro tasks, right? So macro tasks are something that is much more complex. Like, for example, you want someone to write a paper for you, right? You want to crowdsource a task of, hey, can you write SIGMOD papers for me? Okay? Or now we're a teacher, we're facing with the task of grading so many scripts, right? Then we want to ask, oh, can someone grade a script for me, right? So for both of these kinds of macro tasks could be difficult, right? And how to manage them is also an open problem. And last but not least, okay, we talk about crowdsourcing systems in a general sense, but in fact, there are also some other special kinds of crowdsourcing, like mobile crowdsourcing, which are based on the fact that the workers at some location and you ask them, oh, can you take some photos of some monuments or museums in Chicago for me, for example. And there are some nice works about G missions and China Cow, okay, which are dealing with this kind of specific crowdsourcing systems. So an interesting question is how the general techniques for crowdsourcing systems can be applied to these systems. All right, so that's all for today, and I hope that you enjoy our tutorial. And because of the limitation of time, let us go to have lunch together. And if you have any questions, we are all around in the conference, and feel free to talk to us. Thank you very much. Yes, quick question. Yeah.
Okay, thank you. I'm very interested in the query optimization in the crowdsourcing databases.
Yes.
And I see that right now there is a very big difference between the traditional core database and the crowdsourced databases. Traditional database, we all know that when you optimize the John query, we want to just lower the cost of the query. That's it. However, I see that in this crowdsourced database, it's not just one criteria. You have 3 criteria in it.
Right.
So I'm very interested. Is it possible you can explain more about that? How do you determine the best join order inside for a given crowdsourced join? How do you do the trade-offs? How do you can you guarantee which one is the best join order? What's the current status of the research?
Yeah.
Okay, thank you very much for this question. Like, as you said, that cross-sourcing query optimization are quite different from the traditional techniques. And to be more specific for your question, like, I think existing work on cross-sourcing are not very focused on determining the join orders. I think let me give you one example from CDB, which is the last system I have introduced. It wanted to like the granularities are different. They do not want to focus on the table level. They want to focus on the tuple level because, as we said about join, it could be we want to ask questions between each pairs of tuples, and if the worker tell us it's yes, we can join them together. Otherwise, we may drop this join as from the results, right? So the first difference is tuple level instead of the table level. And that is a very key difference between the traditional ones, right? Okay, and the second one is about the optimization criterions, right? For each individual tasks, we do not want to reduce the number of the tasks we want to ask. We also want to reduce the the total latency, right? That is could be the second techniques I mentioned from the CDB, like partition the entire graph into several connected components, and then ask the questions of each components in parallel. So that could be the second difference from the traditional ones. For the quality control, there could be some kinds of techniques mentioned by Yudian and Cheng about how to optimize each individual questions. So I think the third difference is there could be some trade-off between these objectives, right? If you want your results to be more accurate, you have to pay more. You have to, and that means you need to incur more cost. And if you want your latency could be as less as possible, you need to pay more, right? So how to balance this trade-off could be another existing challenges which are not very much covered by my part. Okay, okay. That's my answer. Okay, thank you.
Thanks. Okay. Yeah.
Okay, thank you. I'm interested in how to build the benchmark databases for the crowdsourcing problems.
How to build? I think maybe we can give some information about the current benchmarks, right? Current data sets, right?
Yeah, in fact, there is some link that we have summarized the existing crowdsourcing public data sets, and we found that, in fact, there are not so many crowdsourcing public data set, especially in terms of the sizes, because you know that you have to first, if you want to do your task, you will collect workers' answers, and you have to manually label the ground truth of your task. And in fact, we have summarized, and in our recent experimental paper, we have collected more kinds of data sets. But in terms of the benchmark, we think that the existing benchmark are really far from perfect, and there is a lot of way to do compare with the existing traditional benchmarks in the traditional database systems such as TBCC or etc. So yeah, you may refer to our link for more details of the.
My follow-up question is that the users are easily affected by their existing knowledge or the information they have in their hand. So actually, when you build up about the benchmark data set for the crowdsourcing problems, it's in generally more hard or more difficult than to build a benchmark for other problems. Because when the users or when the workers, they answer the questions, they just answer these questions very subjectively. So the information in their hand or on the screen actually affect their decisions so much. So when you think about this, then the benchmark data is more difficult to build in general.
Yeah, that's also a very good question. So when you talk about some kind of factors that is out of the task itself, for example, some user interfaces, how you will present the worker with the, yeah.
So in my mind, so for crowdsourcing, we usually focus on objective question. It's very hard for subjective question. This is not for crowdsourcing. So the second point is that for benchmark, we want to reproducibility because there are lots of work, lots of papers. It's very hard to produce the results. So how to reproduce the results is another challenge. So I agree that the benchmark is still a big challenge. So I think in future work we can focus more on this part. Thank you. Any other question?
Yeah, you can find us offline, right? And thank you very much again.
Do you need